Hello everyone. I am Enrico Pozzobon from this sector. Today I have to give you a presentation about automated fault injection attacks on embedded devices alone, because my colleague Nils was not able to be present, but he also worked on this together with me. Today there should be a video there that didn't work, but I'm one of the founders of this sector. Our focus is automating ECU penetration testing, so ECU, automotive electronic control units. So fault injection is not our usual focus. Usually we focus on automotive diagnostic protocols and penetration testing on those. So you could say that so now the video loaded. So you could say that fault injection is my passion, but not my usual focus. So our first attempts at fault injections were with voltage glitching, but this was really hard because it required heavy modification of the target. As you can see here, we had to remove all the components to make this fault work. We had to add additional connectors. Not only that, the fault was temperature dependent, so we needed a temperature sensor there to figure out what was the temperature. I had an automated setup there that with my hair dryer would bring the temperature to the will bring the temperature of the processor quite high so that the fault would work. And we ended up even having to build our own PCB so that we could perform side channel attacks and fault injection on this. So it was quite a lot of work, very hard to automate. So we decided to later switch to EMFI, or electromagnetic fault injections, which has some advantages. Like, for example, we don't need to modify the board at all. We can just go there with our electromagnetic fault injection device. So the first time we tried to do some electromagnetic fault injection, we were targeting this gateway ECU from a popular German car manufacturer. It's the root of the network, so everything, it decides where all the packets go, and it is also the trust anchor for certain services like timing, and it's part of the trust anchor for the immobilizer as well. So it's quite a high-value target, and the main processor, the processor that does a lot of the work here is this MPC 5748G by NXP. It is automotive safe and secure microcontroller, and even if they weren't the sponsors here, I would say that they're right about it being safe. It is really durable. It's basically withstood every single at least it didn't break after everything we threw at it. We tried with huge voltage spikes, and it just doesn't break. And we cannot say the same for other automotive parts manufacturers. So what makes a microcontroller unit automotive? So first of all, it should be tolerant to a wide range of temperatures, a wide range of voltage transients, electromagnetic spikes. Also, it's very hard to find it if you try to buy it on a store, and usually it costs a little bit more than the non-automotive counterpart. But other than that, it's pretty much the same. So you can apply everything I'm going to talk about today to most microcontrollers. And the first thing we tried, since we had a target that uses the MPC for 5748G, was to try one of the many already published attacks for similar microcontrollers. So at first we tried this safety is different from security white paper from Riscure, where they attacked the DCF record loading, so the device configuration records. And this worked on the development board, but at least for us, it didn't work on the real-world target. So this was out of the question. Then we tried the Bam Bam attack by Colin O'Flynn, and unfortunately, this only works on the devices that have this BAM, boot assist module, but it actually doesn't work on later devices where the BAM was replaced with this different module. And our target was an example of one of these. And then we looked at other attacks where the attackers were able to obtain code execution on ECUs by modifying the instruction flow by corrupting the program counter. And these attacks, for example, here we have an example on ARM. These attacks usually work by causing a bit flip in the instruction that is fetched from the program flash. For example, on ARM, we see this instruction here has it's a load. So the first instruction on the top, it's a load of a value from a memory location which is pointed by R4 and with an offset of 4. And the result has to go in R7. And just with a single bit flip, so we are hoping to cause this bit flip with fault injection. This instruction is transformed into a load into the program counter instead. And you can imagine also that this kind of instruction, this load instruction, is present in a lot of routines. So mem copy, mem compare. So this kind of instruction is executed all over the firmware and all the time. So even if we shoot our faults at random, we are very likely to hit one of these instructions and possibly to cause a corruption of the program counter. Unfortunately, this didn't work for us because on PowerPC, this is not possible, basically. Well, at least not directly this one, because the program counter is a different register from all the other ones. It's a special register. To move data to the program counter, we need a special instruction that has a very different binary encoding from the normal load instruction. So the probability of getting this to work on PowerPC should be quite lower. Then next we looked at this entire class of attacks, which is the wild jungle jumps. Basically, the concept here is that if the attacker can control a wide enough area of the memory map of the target, we can just jump, we can just corrupt randomly the program counter to jump somewhere where we control the memory. However, these were considered to not be very exploitable in outside of laboratory settings for some reasons. Well, usually the attacker cannot control a large part of the memory map. However, this is not the case for automotive targets, because we have a standard here in the automotive world which is called UDS. In particular, this ISO 14229 whatever. It standardizes the communication between the ECU and the repair shop tester and how the flashing procedure is done. So how the update process, it defines the update process for automotive ECUs. And I will go quickly into how this works. So first, the ECU is normally running in this application mode. So it's just running the application. The program counter is in the application area of the flash. Then at some point the repair shop tester puts the ECU into a programming session. So it switches the state of this ECU into programming session. In this state, the ECU is running from the bootloader instead. Then there is a security access step, which is a cryptographic challenge response algorithm. This should not be considered big wall or a big security feature, because this can be solved. The security access can be solved by any official repair shop tool, which they are promptly leaked on car tuning communities all the time. At least for all the German car manufacturers that we looked at, either we find the repair shop tools leaked on torrent, such as, for example, these ones that you see on this slide, or you even find the security access algorithms reverse engineered and solved on GitHub. And so the problem here is that all of the secret material, all of the secret keys, they have to be leaked, they have to be released into the repair shop places, because they could be offline. They don't have don't necessarily have a stable online connection. So they need to be able to reflash cars even when they don't have an internet connection. So all of the secret key material is stored locally. So after we obtain security access, we can, there is a step called the write fingerprint here, which is just a repair shop write the fingerprint of the repair shop itself to tell who was the last person to flash the ECU. It doesn't really matter what you write there. The important next step is the erasing of the application from the ECU. Now, the erase routine to perform this erase, sometimes it's transferred over UDS, but it's usually are authenticated with strong cryptography. So, for example, some RSA cryptography. So, this is somewhat secure. The erase routine is signed, and the signature is verified using the public signature of the manufacturer. Finally, after the memory is erased, we transfer the new application payload, and then the firmware will internally verify that this application that we delivered is authentic. So it will do, again, a verification of an RSA signature. And if the signature was okay, it will write down somewhere that the application was correctly verified. And finally, we start running from the application, space. And of course, if the verification of the signature fails, this Boolean flag that says that the signature is invalid, will say, that the signature is not valid, and therefore the application will never run into the corrupted application will not run. So our, what we would like will be to be able to jump directly to the corrupted application, to our exploit firmware. And if you notice, this looks exactly like the best case scenario for a wild jungle jump attack. So this is the perfect situation for this. Note that we are controlling around 4 megabytes of the address space, because the flash on this device was 4 megabytes. And this is approximately 0.1% of the 32-bit address space of the processor. So if the program counter is corrupted to be any of the addresses that we control, we could potentially jump to our exploit firmware. So this is the plan, and there are some parameters that need to be set in order to be able to inject a successful fault, in order to cause a corruption of the program counter. These are the typical parameters for electromagnetic fault injection. We have the injection coil itself, can have a different shape, size, direction of the turns, so clockwise or counterclockwise. The position in space of the injection coil on top of the target. Then the duration, for how long we are activating the injection coil. The voltage that we charge the capacitor that is connected, that is then going to be discharged into the coil. And this determines effectively the intensity of the fault. And then we have some kind of timing offset from some trigger signal. and then the memory state of the target, which is affected by all the instructions that we sent all the communication that we sent over UDS to the ECU before injecting the fault. And as a trigger, we tried different triggers, and one possible trigger could be the reset signal itself, so that we inject a fault sometime after reset. This sometimes works. However, usually it takes some time for the target to reset, so maybe it's not so fast. Another trigger signal could be a message that we send, so a CAN frame that we send to the ECU, or some serial command that we send over UART to the ECU, and then the trigger could be that. And we would like to have a some trigger that corresponds to some deterministic code execution that has a deterministic execution time. But this is not always the case, especially for this automotive ECU. It wasn't running some deterministic operating system at all. Again, we would like to have a trigger that we can trigger multiple times a second, and ideally something like 5 volts per second, or as fast as our coil can charge and discharge. Note that all of these parameters are very easy to automate. So position, duration, voltage, offset, and memory state. We can basically automate all of these by scripting. The position can be automated with a CNC mill, CNC machine, and to position our injection head. Everything else is easily controlled in software. And also note that these other parameters, the injection coil shape, the position, the duration, and the voltage, these only depend on the hardware of the target, basically. They don't depend on the target software at all. So we can train these parameters on a toy example that we can build, and then we can transfer our knowledge directly onto the real world target. And we only have to tune the two missing parameters. So this is the first time, our first fault injection setup. You can see this. Actually, no, this is not the first version, but you can see it's a nest of wires. We have a Raspberry Pi connected to some relays to turn on and off the ECU. We have a chip whisperer husky to generate the delay from the trigger. We have an FPGA, some custom FPGA bitstream there, just to generate the trigger from the CAN signal, because we couldn't get a signal on a specific CAN message on the chip whisperer. Then we have a chip shouter, which can be moved by a CNC machine. And all of these is quite cheap. So I think that the cost of the full setup was around, I think, 5,000 euros. And the most expensive part here was the chip shouter, by far. Later we tried to replace the chip shouter with the Pico EMP, but that one needs a little bit more voltage, I think. It doesn't emit faults that are intense enough for now. But yeah, it can definitely be made cheaper. And then what happens after we inject a fault on the target? We can have either a normal response, meaning that the frame that we sent in our trigger as our trigger, it just gets a normal response. We could get a corrupted CAN response, or we could get that the ECU resets and doesn't respond to us at all. What we noticed, and what was really interesting for us in the beginning, was that this specific ECU that we were looking at had UART traces emitted every time an exception interrupt was hit. So an exception interrupt is something that the processor calls. So it's a small piece of code that you can write in your firmware that the processor will call every time an undefined, unexpected situation happens. For example, a division by 0 or the processor is attempting to execute invalid instruction according to the instruction set of the processor, or let's say like the memory could not be read, or when attempting to read the memory, the CRC check failed. By the way, this ECU had a fully ECC RAM, so when that failed, it will also call this stack trace emitter. And this is not very common. Not every automotive ECU does this, but this was very lucky for us because it allowed us later to reproduce this on other targets. But we'll see later. This is an example of how one of these stack traces looks like. We have the value of all the registers at the moment of the crash. And we have the stack trace at the bottom. So the return address of all the functions that were called. And more importantly, we have some registers here, some special registers here, one of which is called the exception syndrome register. Somewhere there should be ESR. You can see it. ESR. Yeah, in this case it's 0. The ESR is exception syndrome register, and there is a bunch of other ones that basically tell us which exception was called, which exception happened. So on the top here you see an exception number. And this, if you look at the manual, correlates with something very specific happening in the core. Now, as I said before, not every ECU emits a stack trace like this, but it is usually possible to source the same microcontroller from an online vendor, flash it with our toy example firmware that does emit stack traces, and then we can train all of the parameters that don't depend on the software. We can train them on this chip. And later we only need to figure out the missing ones when we attack the real hardware. Now, when I'm saying that each of these exceptions correlates with some internal component of the microcontroller, this is what I mean. So here we have a nice picture of the silicon die provided by Olivier from Explained. I don't know if I placed it right here. It might be flipped, but it doesn't really matter. It was just to make the slide nicer, I guess. But what we have here is that we have probability plots where the yellow parts, the yellow squares show the positions with the highest probability, and the dark blue squares represent the positions with the lower probability. So in this, in the top right, you can see that most of the surface is yellow for the no effect plot, meaning that if we hit those areas with a high probability, nothing happens. So we don't have any unexpected behavior. The processor responds normally. Now, in the bottom left, we have an area that has quite a high probability, let's say 1%, that when you hit there, with every other parameter uniformly distributed, if you hit in the top right there, you cause an unexpected CAN response. So the response from the CAN bus was corrupted. This is not super interesting for us. I mean, maybe we cause something bad to happen during the execution, but it's more likely that we caused the CAN peripheral itself to fail. So this wasn't very useful. In the bottom, in the center, you can see that there is some probability. There is quite a high probability, 90%, of causing a reset without any stack trace if we hit in this area in the center right of the processor. We assume that probably that is power supply, maybe, because it basically kills the processor. It kills the processor instantly without leaving it time to produce a stack trace. And finally, in the top left, we can see that there is a high probability of getting a reset with a stack trace. And here we can see even more plots with descending probability. Now, what I would like to highlight is that there is only one small square in the bottom right that correlate that when we hit there, we have a very, very tiny probability when all the other settings are uniformly distributed of causing a jump to our unsigned payload. And another thing that I would like you to note is that a lot of these probability areas are correlated with each other. So we have the illegal instruction highly correlates with this alignment exception, which highly correlates with the jump to payload. So there is some kind of logic here where we can figure out that if we are hitting an illegal instruction, it's very likely that we are hitting something related to the CPU inside the MCU, and therefore, we have a high probability later of causing an alignment exception. So the program counter was misaligned, not at a multiple of 2, and this has a high probability of being correlated with the corruption of the program counter, and so on. There are also some other plots that I could show you, but I think I'm running already out of time. This is other interesting data leakage that you could extract through these stack traces. We can see all the values of all the registers, so we can leak the value of the link register to know where the execution was in the firmware at any moment in time. We can also see some special values, like for example here we started seeing the constant of the SHA algorithm, which indicated that this ECU was using the SHA-1 algorithm. Oh, by the way, I think I forgot to mention that all of this was done without knowing the firmware of the ECU, so we couldn't target a specific instruction. We were quite blind. It was a black box attack at this point. So we developed this search algorithm we called the evolutionary fault injection settings search algorithm, EFISA for short. It uses genetic evolution, so it's a genetic algorithm. I think it may count as AI, but maybe not. You tell me later. But so the idea here, initially the idea was to maximize the variety of different feedbacks to try to explore as much as possible the search space and find different results from the fault. But later when we figured out that all of these probabilities are correlated, later we focused on a different thing. We focused on correlating with searching faults that are correlated with the successful jump to payload. And the reward for this genetic algorithm is determined from the stack trace itself. So some notes about the optimization of this algorithm. Some parameters take longer to change than others due to physical constraints. For example, moving the CNC machine takes quite a long time compared to changing the time offset of the injection. So we try to group together the parameters so that we can have the highest possible fault injection rate. So as I said, some feedbacks correlate better with the code execution than others, so we try to search for those first. And the interrupt handlers, this is obvious. The interrupt handlers, these stack traces are used as a feedback channel for our evolutionary algorithm. So the structure of our exploit firmware obviously needs to look something like this. We have most of the code, most of the area of the flash will be just jumps to our exploit payload. In reality, it's not just jumps. There is NOPs interleaved. There is a reason for that. But basically, the idea is NOPs in PowerPC VLE is only 2 bytes, just like in ARM thumb, but a jump to a far address is 4 bytes. And if we were to jump in the middle of a 4 bytes instruction, that would not be it will not successfully jump into our exploit code. So we try to use as many NOPs as possible and interleave it with a few jumps to our exploit code. The exploit code is kept very, very small. Ideally, we have only a stub that receives and sends write and read commands from CAN or UART, but then it depends on which kind of interfaces we have available on the target. And the performance of this search algorithm looks suspiciously like the cumulative distribution success probability of any randomized attack, really. But it's actually much faster than a random attack. It is, it takes around, from this plot you can see that it takes around 10,000 faults to start getting the success every time. So this plot was made by every time starting the algorithm completely from scratch, losing all of the knowledge that it previously had. And we saw that on average, it took 10,000 faults to get there. Half of the time it took less, and half of the time it took more. And this is pretty good, I think, because we are injecting around, as I said, on a good target, we are injecting 5 faults per second. We are mostly limited by the chip shouter itself, getting hot, and that is our limitation. Program counter corruption on PowerPC, as I said before, doesn't look like ARM. In ARM, you can just flip a couple of bits to turn any load instructions into a jump instruction to an address that can be controlled by the target. However, on PowerPC VLE, which is a instruction set that was used in our target, and in a lot of our targets, this is not the case. So program counter has a completely different instruction to write it than all the other registers. So less probability of randomly hitting one of these instructions. Also 00, FF, all of the classic values that you can use fault injection to cause to be loaded into the instruction, they are invalid instructions. So, for example, on ARM, if you manage to send a fault that makes the instruction fetch a 0, that is considered a valid instruction, that is considered effectively a NOP, at least on ARM thumb. Forgot about ARM proper, but 00 in a lot of architectures, it's just a NOP. So that means that we can instantly skip instructions. In PowerPC, this is not the case. But obviously, we were successful at jumping to our unsigned payload in our target. So, what was the cause of this? How did we obtain this? So, most of the time we figured out that we were misaligning the stack pointer. Basically, every time you call a function in any programming language, in every architecture, you have to create like a stack frame is created for you, and then when you return from that function, that stack frame is destroyed for you. The creation of that stack frame is done by incrementing and decrementing and incrementing the stack pointer, which is R1 in the case of PowerPC. And if you manage to misalign this by corrupting the instruction that is adding or subtracting from the program counter, from the stack pointer, then on the return from the function, the link register loads the wrong address from the stack. Potentially something that the user is controlling. And then when the next function returns, you are jumping to an address that is controlled by the attacker. So we have code execution. What can we do with it? We can dump the flash, but remember we erased the flash to run this attack. We were running only from the bootloader, basically. So we can only dump the bootloader, which is still interesting. We can still get a lot of knowledge from the bootloader, but it's not as good as dumping the firmware. We can uncensor JTAG on a lot of architectures. Like, for example, on PowerPC, you do this by writing a DCF record, so a device configuration format record. And after you uncensor JTAG, you can write, you can do other stuff, even permanently after you already run the attack. You can access the HSM API, so all of the secret keys, that stuff that is stored in the HSM, you can not read them directly, but you are running code on the host processor, so you are able to send queries to the HSM, so you can use those. We didn't attack the HSM itself for this processor, even though now we are doing this attack on an HSM, but that's going to be under NDA, because you might know NDAs are very hard to get documentation for without an NDA. So probably we're not going to publish that. And regarding replicating this on further targets, so we want to automate this on as many targets as possible. So if the target has detailed stack traces like the one we saw, it's very, very easy to just automate this entire process. Just have create a parser and a rewarding algorithm for specific to your target, and then just put it in the EMFI glitching setup, and you're probably gonna get a fault within an hour. Like a code execution within an hour, at least if the target doesn't have special protections against EMFI, but we didn't see those yet in our targets. If the target doesn't emit stack traces on exception interrupts, then you need to do the trick that I was talking about before, getting an empty MCU, write your own toy example for it, get the parameters out of that, and then use them in the real target. Couple of other slides here. How about ARM? What about ARM? So ARM is so the next generation of the ECU that we were looking at will use ARM. So we wanted to look at how good or bad ARM is when compared to PowerPC, and we saw that there is around 100 times more probability, at least for a similarly priced processor and with similar specifications. It was around 100 times more likely to get code execution, and it was extremely fast to get it. You didn't even need to aim that well. Just spraying random electromagnetic faults was already almost enough. You could have done it with a random attack on this processor. So this was sad to see. Maybe when it's actually soldered on a real automotive ECU, it's gonna be better. And also regarding the results, we tried this until now. We did it on 5 different targets. It was successful on all of them. So 5 different ECUs from like 3 of the MCUs usually used on these ECUs were from 3 different MCU manufacturers and used 3 different architectures. And yeah, we will continue to try these on other targets. In summary, fault injection can be easier than it seems, and also cheaper than it seems. You just need some luck. You can improve your luck by using the right algorithm if you have the right feedback channel. The attacks are almost completely automatable. Outside of the physical setup, of course. No firmware reverse engineering was required for this on any of the targets. For one of the targets, we had the firmware, but we didn't need to look at it because, some hardware reverse engineering is necessary because you need to know which MCU you have and what is the memory map of this if you want to develop an exploit for it. And the attack is very low effort, just like this presentation. Because the only hard part is developing your training firmware, your toy example firmware, if your target doesn't already emit stack traces. And for mitigation, you can try to use the memory protection unit, so enabling something like write or execute, and running the bootloader in the HSM might help. We don't have publishable results about that yet. We saw some manufacturers are running their entire bootloader in the HSM, which has worked to stop us for now. And or you just revise the update process to authenticate the whole firmware transfer, because the problem here was that we were able to control a large part of the flash. So a Boolean flag that tells you can you execute it or not is not enough. you need to authenticate every single write. So something like TLS should work here. Okay, thank you for your patience. If you want to contact me or the company, you can take a photo here. And other than that, I'm here for your questions.
Thanks, Enrico. And let's see, do we have questions in the audience? Yes, we do have.
So I wasn't clear. You said once you had arbitrary code execution, you could re-enable JTAG. Was that JTAG a persistent re-enablement, or was it only for one boot?
So in the case of this issue that we were attacking, yes, it was persistent because we used, so once we got code execution, we could write to Flash. The Flash has these device configuration files, DCF records, where basically you can, it's a one-time programmable memory, but you have a lot of the later records override the previous records. So if you have a record that censors JTAG, which was already there in the MCU, you can add a new record that uncensored JTAG, and the last written record always has priority. And in this case, it was possible to re-enable it. That is processor dependent, because on other processors this is not the case. There are ways to permanently censor JTAG. Okay, and then once you could re-enable the JTAG, could you just flash down the original firmware and dump it via JTAG? Yes. Okay. Well, no, flash any firmware, but not the one that we erased, because we didn't have that. They didn't have any other. Basically, you had no other options for like getting a firmware update from somewhere else to put back on, right? We were able to get firmware updates, but not exactly the same file that was there, because you can get from repair shop software, you can extract a lot of firmwares there, but not the exact one that was running before.
Okay, one last question for today. Anyone? Yes. Yeah.
Hello. At the beginning, you told us that you had the code of the bootloader. So how did you extract it actually, the bootloader?
Sorry, can you repeat the question?
The bootloader. You know the instruction in the bootloader. So you were able. You know which instruction is executed in the bootloader?
No. You mean probably this slide here, or well.
If I understood correct, you have the firmware of the bootloader.
No.
Okay, thank you.
We don't have the firmware of the bootloader. At the beginning, we didn't have the firmware of the bootloader. So we didn't know which instructions we were attacking. We just randomized the time. Also, it was really hard to, even if we had a specific instruction to attack, because the timing of the execution of this firmware was so undeterministic, it was not possible for us even later to target a specific instruction, at least with the limited trigger capabilities that we had. Yeah.
All right. And on this note, we'll ramp it up for today. Let's give a warm set of applause to Enrico.
Thank you.